I just used AI to optimize immunotherapy treatments by getting it to predict a patient's response to immunotherapy and being able to pinpoint the most effective immunotherapy treatment for a patient. But how? Well, let me break it down for you. You see, when fighting cancer, there are three main treatments that oncologists use: chemotherapy, radiation therapy, and immunotherapies. Now, immunotherapies is this new branch of cancer treatment that basically supercharges the immune system to identify and kill cancer cells when it sees them. And the reason why immunotherapies have shown promise within the cancer space is because it offers the ability for long-term control of cancer, meaning that the immune system will be able to identify cancer cells whenever they come up throughout a patient's lifetime. And in some cases, it can even result in permanent protection against cancer for a patient. Now, although this may seem really good and all, only 15 to 20% of patients actually respond to immunotherapy treatments. That means that 80 to 85% of the total population that is given immunotherapies do not respond. Say what? The reason why is because oncologists have to calculate too many factors like patient demographics, predictive biomarkers, tumor mutational burden, and tumor microenvironment, among others, to formulate a good treatment plan for a patient without even knowing that they'll respond. And currently, oncologists are swarmed with so much data, so many data points from patients, hundreds of patients that they have to take care of, and oftentimes leads them to taking weeks to even formulate a treatment plan for a patient. Now, when I saw this problem, I knew that if I could draw on my skills that I've developed in artificial intelligence and apply it to this problem to create some sort of model to tackle this, I would be the one to fix this problem. You already know who I am. Hey, I'm Arjun, a 16-year-old from Toronto, Canada, working at the intersection of AI and oncology, and this summer I'll be interning at Triage to showcase some of my skills and apply them to real-world projects. And so after 3 weeks of hard work, of learning new models, developing new machine learning architectures, I have finally completed the model. Let me explain to you how it works. I'll start with the first model, which takes in a bunch of features to predict whether a patient will respond to immunotherapies on 4 different degrees: complete response, partial response, stable disease, and progressive disease. For this model, I utilized XGBoost, which stands for Extreme Gradient Boosting, which is basically a supercharged decision tree model. And you can think of these decision trees as little flowcharts branching off from each other until they reach a final outcome. In our case, the 4 different types of a patient response. Now, for XGBoost, the tree starts at the root of the node and branches down to internal nodes based on feature attribute values, which eventually leads to leaf nodes where the predictions are made. But the really cool thing about XGBoost, and the reason why I used it, is because it keeps going back and asks more questions to fix the decision trees and the questions that it made in order to improve the accuracy of the model. For example, a question the model might ask is, if this specific genetic biomarker leads to a patient responding to immunotherapy. If the answer is yes, then it'll keep continuing. If the answer is no, then it'll go back and ask another question. Now, XGBoost also uses gradient boosting. And this is a process of sequentially building trees, with each subsequent tree aiming to fix the errors made by the past. And this iterative process is continued until a predefined stopping criteria is met. Again, this is super cool because XGBoost goes back and fixes the errors that it made in order to ensure that the weak nodes become stronger and resulting in a greater accuracy. Now for the second model. And this model aims to pinpoint the most effective immunotherapy treatment based on some clinical trials that I gathered together. And for this model, I used a new neural network architecture called TabNet. TabNet is also really good at working with nonlinearity, and in order to reach the outcome of a specific treatment to use, it would have to solve this problem nonlinearly. So after the data is inputted into the neural network, it reaches the feature transformer layer. And here, the model encodes the categorical features into embeddings, which are basically dense vector representations. It also applies some initial transformations to numerical data. Now, this information is passed into the best part of TabNet and what makes it really unique, the sequential attention mechanism. Essentially, the model will look at a different subset of features or columns at one step at a time. And then with each step, the model divides features into which are the most important and which are the least important. Now, the ones that are the most important, the model will pay much more attention to. And it can do this with what we call decision steps. With each step, this model splits the features into two groups. One that it'll pay attention to, and the other one that it won't. The one that it won't will be masked or ignored for that step, and the features with the higher importance scores are kept. Then this data is now fed into the last layer, the output layer, which results in the output, in our case, multiple immunotherapy treatments. And although I'm just some random teenager that made this project in the room, these models actually have a lot of potential to impact the immunotherapy space. And there's close to nothing right now in hospitals that can currently predict a patient's response to immunotherapies and also pinpoint the most effective treatment for a patient. There's also no model currently that takes into account these many features. With the models combined, the dataset contained over 200 features or columns that the models were trained on. With this tool, oncologists can now calculate a patient's response and figure out what the best treatment could be, this is the recommendation, in a matter of seconds. And this is huge because now this reduces the error of oncologists calculating a treatment plan while also saving them huge amounts of time, which is crucial in a setting like a hospital. Now, if you found this interesting, be sure to follow me on my LinkedIn, subscribe to my YouTube page, and follow my Substack for monthly updates that I post where I showcase my new projects and new experiences and reflections that I'm having each month. And I'll see you next month once I present this project in front of professors at the University of Toronto.